Okay, today is our great pleasure to have Alessandro Roggero from Trento University. Ali will tell us quantum error correction codes for lattice gate series. So Ali, please take it over.
Awesome. Thank you, Shayu, for the introduction, and thank you for the invitation giving this talk. It's especially nice to give the talk about this to you guys at InQubator, because this line of research sort of like started in the hallways where you're sitting right now, like 4 or 5 years ago. It's nice to tell you about like the updates about this. So what I want to try to cover in this next like hour or so is try to make a parallel between lattice gauge theories that are possibly of interest for a physicist and quantum error correcting codes that are useful to correct errors in quantum devices. Okay, so given the audience, I will be very, very brief for the general motivations. So like we know that there are a large number of systems in fundamental physics, can be like nuclear particle physics, that are described as strongly interacting many-body systems where classical simulation methods are extremely challenging to pull off. This could be like jets in high-energy collisions or scattering properties of nuclei, for instance. And part of the reason why a place like the InQubator is going is that we do believe that like performing digital quantum simulations on this type of systems could be beneficial in some situations. Okay, so with that in mind, okay, one of the things you would like to know is like how close are we to try to simulate something that looks like a collision at CERN. Okay. A useful way to sort of like visualize the path towards useful quantum computing is to look at this two-dimensional plot, where we have on the x-axis the size of the quantum computer. It's the number of qubits we have in the actual device. On the y-axis, we have the error rate, okay, which you can think of it as sort of like giving you an inverse coherence time. So the more like to the bottom you are on the y-axis, the longer you can make the coherence time. So say like 10 to the minus 2 error rate tells you that you can do about 100 gates before running into complete noise. Okay. So what you see here, it's a depiction of like in purple. These are regions either at like small system size or at small gate count, where that are easy to simulate classically. While down here, okay, in the tens of thousands of qubits is possibly where we would like to see to start to do like some applications in nuclear physics, nuclear and particle physics. Okay, so in order to try to get there, okay, one of the important things is that it's complicated for hardware manufacturers to reduce the error rate in a constant fashion. So you see an horizontal line over here. This is the error correction threshold. And the idea is that part of the reason we believe that digital quantum computers can be helpful in tackling some of these physics problems is that for devices that have good enough fidelity, so where the error rate is below a given threshold, we can use error correcting techniques to boost the logical error rate and be able to calculate, to perform very large simulations without reducing the actual physical error rate at the same point. Okay, and the idea is that we need to essentially trade off a number of qubits for gates to be able to achieve that. Just to give you an idea of like where devices that are available are, in 2019, 2020, more or less when the incubator started, that's where the devices that are available in markets were. The quality and size of devices has been improving dramatically in the past few years, both on quality, so like pushing down on this y-axis and pushing to the right. Okay, and more recently, we have now devices with like 10 to the minus 3 limiting error rates and hundreds of qubits. Okay, so right now it's not uncommon to see calculations using, say, a few thousand gates and tens of qubits. These are sort of like routinely done at the moment. Okay, however, we still want to try to keep pushing to try to go to the goal of like performing quantum simulations. of standard model physics. So in order to do this, as I was trying to say before, having a protocol that allows you to correct errors and improve the logical error rate is very, very important. Okay, if you really want to push to like large enough systems. So the estimates that you see in this plot here, so this 10 to the minus 2 error rate and these millions of physical qubits to do useful things are based on sort of like quantum error correcting code, which is designed to be general purpose. Okay, so the point of what I want to try to do today is to try to show you that like if one has a specific sort of like physical simulation in mind, we can design quantum error correcting codes that take advantage of the structure of the physical problem we want and try to reduce the actual physical requirements. Okay. So before getting there, let me just briefly remind you of like classical error correction. Okay. So the basic idea is that in the classical setting, at least, okay, we have a bit of information, okay, that we want to preserve. The bit of information in general can go through, interacts with the environment, goes through something, through a noise channel, and exits as a B prime. Okay, so for a single bit, we have only two possibilities that really matter. We either have no errors, so that like B prime, the bit after the channel is the same as before, or we have one error up and then the bit gets flipped. Okay, so one way to preserve the logical information contained in this bit, at least one of the ways, is to encode information in a redundant way. So the simplest thing you can do is to use what is called a repetition code. You take your bit, you copy it in 3 bits, you send all 3 bits through the channel, okay? And then after the channel, you get the B primes for all of them. You apply a decoder, which is chosen so that for low noise strengths, you can recover the logical information. And the idea here, for instance, imagine that you do as a decoder a majority voting. So you take the bit which is the most frequently occurring among the 3, that allows you to fix one error. Okay, the idea is that if you start, for instance, so with 0 errors, you just have a string with like the same bits. With a single error, you have one of them which get flipped. And by doing majority voting, you're able to reconstruct the right guy. If 2 errors happen, okay, the majority now it's on the error side, and then you are encoding the error. By doing the decoder, you're actually like thinking of you're going to reconstruct the wrong bit. Okay, so this tells you that like one, you need redundancy if you want to be resilient against error. And 2, depending on the encoding you're doing, there is a threshold amount of error you can sustain and still win out of this game. Okay. Of course, like if you want to then use this bit to do things, okay, you want to manipulate this bit or collections of these bits and apply this cycle of like so encoding and decoding over and over and over again. Okay, and you want to do it like at a rate which is fast enough so that only on average 1 error happens within every of these blocks. Okay, otherwise you're not gonna be able to preserve the information. Okay, so the reason why I brought this up is because sort of like simple quantum error correcting schemes really work in the same spirit as this. Okay, so the basic idea is that we do want to introduce redundancy. Okay, but we have one of the issues is that if I'm giving you general, even like a single qubit quantum state which you don't know, you cannot copy it. Okay, so there is the non-cloning theorem. So one of the ways that we can think of applying this instead is sort of like copying the system, setting up the full evolution in a larger qubit space. So we start with more qubits in the first place, okay, and we never like make it increase. We just work in a larger space as we go, okay. Then if we want to find an encoding, okay, a useful encoding. So for instance, what we are doing here, we are copying a bit to 3 copies of the same guy, okay. One way of obtaining exactly the same thing in this larger Hilbert space is to impose external symmetries. Okay, so we can, for instance, like impose that like the parity of every pairwise couple of these guys here is always positive, for instance. This ensures that like the only logically valid bit strings are the ones where you have 3 repetitions of the same guy. That does essentially the same thing as the encoding we had before. Okay. And the idea is that since we need to specify a symmetry to characterize the logical bit strings, then when we want to correct errors, okay, we can measure the symmetry operators, which will leave the logical states untouched. but will affect the error states, to try to reconstruct the error that happened and essentially perform the majority voting we were trying to do before. Okay, so that's a basic scheme of what is called quantum repetition code. Okay, and what is described here, it's really just a classical code, because you're only fixing one type of errors. You can think of like bit flips, for instance. Okay, it's just a classical repetition code, embedded into a larger Hilbert space. So we are working with vectors in a Hilbert space, okay, which is the natural setting for a quantum mechanical system. So more in detail, let me just try to give you like a concrete example of this. Imagine you have one qubit and you want to preserve it in time. What you're doing, instead of like setting up your calculation with a single qubit, you're setting up in the Hilbert space of 3 qubits, okay? And then you choose 2 commuting operators, 2 commuting symmetries, okay? In this case here, it's the Pauli Z on the first qubit and the second symmetry is the Pauli Z on the second and the third. Okay, these 2 guys here are specifying the symmetries you want your state to be invariant with, which means that you want to only keep states. So the size of the space that you want to store logical information, it's size 2, right? If we are using these 3 copies, we have 8-dimensional space. Okay, each one of these guys has 2 eigenvalues. If you want to go down again to a 2-dimensional logical space, we need to impose 2 of these guys. Okay, so we can choose, for instance, to consider logical only the states with, say, the +1 eigenvalue on both of these symmetry operations. And that tells you that the 2 logical operations correspond to 2 logical states corresponding to the 0 and the 1 are exactly the 3 copies that we talked about. Okay, so that's essentially like one way of implementing the idea of like doing the repetition code on a quantum computer. And of course, like this trick of like measuring symmetry operators, okay, without disturbing the system and using the outcomes to fix this is what is described in this diagram here, okay? The important thing to keep in mind is that when you're doing quantum error correction, you don't want to measure your system because that's going to collapse it. What you want to do, you want to use external degrees of freedom, like additional qubits, to try to extract the eigenvalues, okay? So in general, you can think of it as like, since what we are doing to preserve quantum information is to enlarge the vector space we're working with and imposing symmetries, okay? Every time you're performing any quantum computation on these encoded qubits, okay, you're effectively performing a gauge theory simulation in the sense that like you're working with a system with an extensive number of local symmetries. Okay, in this particular case here, it's a very simple gauge theory, right? Every triple is detached from everybody else. Okay, but the idea is that gauge symmetries and stabilizer formalism of quantum error correction have they have things in common. Okay, so they are both essentially like specified by local symmetries. Okay. So to try to go closer, okay, I'm getting very slow. To try to get closer to like lattice gauge theories from the other side, let's just take as a very simple example, 1 + 1 dimensional U1 pure gauge theory, okay, where you have a collection of links, sides are always empty, okay, you have electric fields on every link, okay, and Gauss law in this particular case here just tells you that like the electric field on both sides of a link needs to be the same. Okay, we can turn this into a symmetry operation by just exponentiating the Gauss law operator, right? And again, we are seeing that like physical states are exactly those stabilized by the symmetry operations. Okay, so in order to make this more similar to like the repetition code we saw before, okay, let me try to like look directly at the physical states across one site, okay? So what I'm writing down over here is the state of the, it's a generic wave function on 2 links across one site, okay? Written in the basis of eigenstates on one link and eigenstate on the second link. You can sort of think of it as like a Schmidt decomposition on the site, okay? Now, if you impose Gauss's law, or if you impose gauge symmetry, that tells you that like the only physically allowed states are those where the electric field components are the same across the link, right? So this already shows that like you do have redundancy just because you're imposing Gauss law, right? You have a copy of a state on both the left and the right of any given side, okay? Which to be physical needs to contain the same state. Now, if you want to do the full repetition code, the easiest thing to do is to just add one link every order, okay? So that across any given site, you always have 3 links, okay? Gauss's law is applied to both pairs, okay? Which means that like in the physical subspace, okay, we always have states which are triple copies of basis states across any given site, okay? So essentially by increasing the dimensionality of the odd links, say, okay, we are essentially turning a pure gauge U1 theory into a repetition code throughout the lattice, okay? So in general, if you want to do this, okay, imagine that you want to encode a full system, okay? And we are considering a number of sites equal to 2n, okay? If you want to do a generic one, okay, you need in general to truncate it. Let's say you're truncating it to L qubits, which means you have a cutoff in the electric field, which is like 2 to the L over -1 if you want. It depends on how you truncate it, right? So the idea is that if you directly use the repetition code, okay, without using the gauge symmetry, the total number of qubits you need to use is 3 times 2n times L, it's 6n L qubits, right? While if you're using the fact that like the physical states that you're interested in satisfies Gauss law, okay, then you can actually like save a lot of these qubits, okay, and only use regular single links on the even ones and double links on the other one. Okay, so this comes with a saving of, let's say, 50% in size. Okay, now something that I went through very quickly is that this code is really only a classical code. It only fixes like X errors, for instance. Okay, if you want to turn it into a true error correcting code, you need to concatenate every one of these qubits into a code that fixes phase flips. Okay, you can think of doing exactly the same thing, but just at the basics. Okay, so what I'm showing you here are cost estimates for a full encoding, okay, of a U1 pure gauge theory with sort of like standard single qubit error correcting codes. So this notation here, 913, just tells you that like you're using 9 physical qubits to encode 1 logical qubit, and you're able to fix 1 error. It's distance 3. Okay, 913 is it's essentially a concatenation of the repetition code I showed you before, right? You use 3 qubits to fix X errors, and for each one of these, you use 3 qubits for a Z error. Okay, that will require 18 times NL qubits overall. If you use the best possible single qubit code that you can find, that's the 513. Okay, that allows you to go down to 10 NL. Okay, but keep in mind that like this one here, it's designed to work for any simulation that is supported on 2NL logical qubits, right? Using the Gauss law code, we can shave 10% of this cost. Okay, so that's one of the motivations for like try to use an error correcting code which embeds the gauge symmetry that you have directly to make it cheaper. Okay. Now, of course, a pure gauge theory, it's sort of trivial, okay? If you don't have any dynamical fairness around here, all the gauge theories, all the gauge symmetry is telling you is that the electric field across sites needs to be the same. Once you fix once, you fix the whole lattice, so there is not really much fun to be had over here, right? So, yeah.
Ali, can I ask a question?
Okay.
So, yeah, just if I consider the Gauss law constraint, and I think I have L qubits per link. Yeah, the Gauss law is basically saying the flux on the E1 is equal to the flux of E2.
Right.
Can you write that constraint as a stabilizer in general?
So we are going to get there in a second. So for the specific case where you don't have any fermions, right? Yeah. So you can think of it like you're using L qubits to encode L bit integer inside of the link. Okay. Right? So equality of bit strings means equality pairwise of the bits.
Right.
Right. So that's a simple stabilizer code. You just check it like you have the same parity left and right. Okay. The same thing, we are going to go through it in a second. We'll apply directly when you do Z2. Okay, when you start to have more than 1 qubit per link, one has to be careful. The short answer is that it's possible to turn it into stabilizer code.
Okay.
But the simplest way of doing it is when you have a Z2 or no.
Sure. Yeah. Okay. Okay. But in that case, there is no fermion. What is that stabilizer that checks the integer digits are equal?
So you can think of it like you really have like 2-bit strings on both sides, which are the same, right?
Right.
So you're looking at parity. So for every qubit, for every bit, you do a Z1, Z2,
Uh-huh.
and the parity needs to be even.
But you, let's see, if I have each link has 2 qubits, right? Then and for the 2 links, I have 4 qubits in the end. The parity checks you're seeing is Z1, Z3, and Z2, Z4. Is that right?
It depends on how you label them. So like imagine that you call like 1 and 2, these 2 guys here, and 3 and 4, these 2 ones here. Then you have a Z1, Z3, and Z2, Z4.
Okay.
Right? That's only enough to do one check, right? If you want to do the full code, you need 3 copies.
Sure. Yes. Yeah.
Right? And either you do it this way, or in this particular case, you already see that like you can go past one more link, and then you just do these 3 guys.
Okay.
Right? Yes.
Okay. Thank you.
Awesome. Of course. Okay. So what I was saying is that pure gauge abelian theory, it's way too simple to do anything fun. So I want to show you how one can actually add dynamical fermions to this. And we'll go a little bit into the detail of this, at least for like the special case of Z2. Okay, so I will start in the general case, again, pretending to do a U1 theory, so that like the Gauss law now is modified by the presence of a possible charge. Okay, we're going to use staggered fermions, so we can say on the even sides we have fermions, on the odd sides we have antifermions. Okay, so the charges are staggered as we go. So in this case here, we can actually allow, depending on the presence or not of a fermion over here, to have a different electric field on both sides, okay, which gives a bit more structure to this. So again, the same notation as before. Imagine we select one site and the 2 links around it, okay? That's the generic state you can have, okay, that you can write down. Where now you see we also need to take into consideration the Hilbert space associated to the site. Now, if we impose Gauss law across this site, this for a given value of the electric field to the left and the occupation number n on the site, that uniquely fixes the value of electric field after the site. Okay. This is not quite a copy, okay, as we had before, okay, but it's reasonably easy, at least for Z2, okay, to perform a unitary operation on top of this state here and turn it into a copy. Okay, a simple idea to see how to do it without worrying about fault tolerance is that since these are the physical state that you're allowed to, okay, if you want to turn this epsilon plus NQL into just epsilon, all you need to do is to do another or a decrementer controlled on the state of this qubit. Okay. Now, doing a controlled decrementer, it's difficult to do fault tolerantly if this guy is more than 1 qubit. That's why we're going to talk about Z2 most of the time. Okay. But that's essentially the idea, right? So we can perform an operation over here which preserves Gauss law, okay, which allows us to expose the copy of the link on the other side. Okay, and again, since we only have 2 copies of an electric field across a site, if we want to do a full code, we need to double it. Okay, at least this is the simplest way of doing it. We're going to get in a second like how to do a bit better afterwards. Okay, so this is the same thing as before. So imagine that now we have again 2 n sites and 2 n links. Now we are also going to need to use qubits for the sites because we have dynamical fermions, right? So that we have in general, and we are going to do a Z2 theory, so that like we really only have a single logical qubit pair. Okay, so this is 4n logical qubits. If we want to like encode all of them using gravitation code, that's going to be 12n. Okay, if we do this mapping, okay, to implement the error correcting code by doubling them, the first thing to consider is that we don't need to replicate the fermions. All the redundancy we really need, it's in the gauge links. So we save in the memory that is required to encode fermions. Okay, we still spend a little bit because we need to increment every other link. Okay, but apart from that, like, so we go from 4n qubits to 5n qubits. So it's not difficult to see that like the gain in this more generally interesting situation is much larger than before. Right. So if before we were winning like 10%, now it's 25% in memory. Okay. With respect to like the best possible single qubit encoding, where by single qubit encoding, I mean, we are using a 513 code for exactly every qubit that we have over here. Okay. Now, one of the nice things about this one is that on top of being cheaper in terms of memory, okay, it's also easier to deal with when we want to perform operations, okay? And an easy way to think about it is like the logical operations that are natural in this code here, okay? They do preserve Gauss law, okay, because they are built so that they are commuting with the stabilizers, okay? While if you want to implement operations in a generic encoding, okay, you need to perform multiple logical operations to form as an aggregate something that is like gauge invariant, okay? And one of the real pains about the 513 is that it is true it's the most compact code, but if you want to do even simple simulation operations like a C naught between two 513 codes, you need to do it into two steps. So you need to perform half of a C naught, perform error correction, do the other half of the C naught and do error correction. So that takes effort, okay? That's one of the reasons why the code which is in between, which is a 713, is more popular than a 513 at the moment, because you lose a little bit in space, but the operations are easier, okay? The nice thing about these sort of like gauge covariant codes is that operations on them are cheaper than not with the best possible compact codes. Okay, mostly because the gauge invariant operations are the natural operations on this code here. Okay, so that's a bit easier to deal with. Now, there is one catch. Okay, so we are winning versus like a generic code which is designed to preserve information locally. Okay, but there is a price we are paying. Okay, the price we are paying is that imagine it like we do a regular encoding where every qubit is encoded with its own error-correcting code. Okay, if we have any error within each one of these blocks independently, we can fix it. So imagine we have a situation where you have an error on this link, an error on this site, an error on this link, and so on, but where you have a single error per block. Okay, with the more expensive encoding, okay, we can fix all of them, because there is always only one error per block. Okay, if we are using the cheaper Gauss code, okay, we win in memory, but we lose in a way in the blocks where we can allow an error. Okay, so in this situation here, we use doubled links. Okay, one can show that like we can sustain a single error, okay, happening anywhere between two sites and the links attached to them. If there is one error anywhere here, we can fix it. Okay. If there is more than one error anywhere here, then we are not going to be able to fix it. For some 2-qubit errors, we might be able to spot that it happened. Okay. But in general, the code is not designed to be fault tolerant past one error. Okay. So if you want, like, we are if in order to use this code efficiently, we need to lower the noise rate for every given patch of the system. Okay. If the noise rate, yeah.
Oh, sorry. Have you calculated how much larger the threshold is for these kind of codes?
That's a good question. We don't have a number for the threshold. The distinction is subtle in the sense that like the physical regions where you allow a single error are different because now you span two sites, right, and links. But the amount of qubits you need in each one of these areas is different. Okay, because like for instance, if you want to do a 913 here you have 9 qubits, while over here you have, what is it? It's 1, 2, 3, 4, 5. You have 15. Okay, so you can think of it like you want to So the real answer is that if you want to find a threshold, you do need to perform a simulation where you have stochastic noise and you check what a threshold is. The quantitative argument, you can think of it like, is the number of error locations you can allow, okay, to have within a given area, okay. That's also like the idea. So here, when we have this double link, okay, if you want to find where the error happened, okay, if there was no site, we can tell in which one of the double link it is. If we have a fermion, we also need to use the next guy to spot it. Okay, so the idea is that the information needs to be preserved as a slightly larger area. The accurate calculation of the threshold, that's something that like should be done. Okay, the idea here is that we do expect like for a Gauss law code, the physical threshold should be a little bit like lower. So we need a little bit lower error rate. Okay. And of course, like if we can live with slightly lower error rates, okay, we can actually do better than this code here, right? Because as I was saying before, we can use multiple Gauss laws together to take the place of this doubling, okay? So we can actually do something that looks like this, where we essentially don't add any memory for the bit flip codes. We just use the regular qubits we have already in the system, okay? And we measure Gauss's laws across all sites, and we combine together the measurement of the stabilizers on, say, 3 sites at a time. In this case here, the actual area is the same because like we don't have to double this. Okay, so this actually turns out to be like more helpful than this one. It's only that like this was easier to explain the construction of the protocol. Okay. So all of this has been in 1D, okay? In general, we can actually make this work in a larger system, okay? So one way to think about like what we constructed here, okay, is that we have for a d-dimensional system, okay, d times m, where m is the number of sites links. So m plus dm is the total number of qubits we have around. Okay. We are using 3 times this many qubits to do the repetition code to store dm logical qubit of information. The idea is that we have m plus dm qubits, but we have m stabilizers, and we have m Gauss's laws, which will kill this one, and the only leftover is d times n, and we can fix every single error. Okay, that's a compact way of writing this thing down. Okay, the gain, okay, depends on the dimensionality with respect to like more standard codes. Okay, the ratio gets a bit lower for larger dimensions, mostly because like the patches we need to consider are a bit larger. But like as a side note, so this essentially only uses m stabilizers corresponding to the Gauss laws, which are always local, right? So like any of these Gauss law touches, it's a product of Pauli matrices, which touches the site and the links adjacent to it, okay? If we allow ourselves to include no local stabilizers, okay, you can actually do the full construction only with a log in space, increase in space, okay? That's sort of like generic for stabilizer codes, okay? This is not special for the Gauss law code. The price to pay is that this might become non-practical in practice, okay? Now, let me say a couple of things about the 2-dimensional case. Okay, so an easy way to think about like the 2-dimensional case, it's that we have a square lattice in 2D where we need to have 3 qubits for every logical qubit that we want around, right? These are used for the phase flip code. Okay, so think of like this blue circle here as containing the 3 qubits that you need to store a logical phase flip site. Okay, when we do the Gauss law code, we want to check it like the parity, so the product of these on all of the links attached to the site, okay, times the Z on the site have positive, have a +1 eigenvalue, right? But since each one of these qubits here, it's already a 3-qubit repetition code, okay? The total stabilizer we have for Gauss law in this encoding will be, what is it, 12, it's a weight 15 operator, okay, which comes with its own cost. Okay, the advantage of this formulation here is that the Gauss law stabilizer has weight 15, but the phase flip stabilizer have weight 2. You can just measure them pairwise. Okay, that's not the only way to do the encoding, okay, because we can actually mix the bit flip Gauss law code and the phase flip regular code, and that's what is shown on the right inside. Okay, we can turn this sort of like very low weight stabilizer for the phase flip and very large weight stabilizer for the Gauss code in average weight guys on both sides. Okay, one way here you can see we can do the 5 Z's you need for the Gauss code for every single collection of 3 qubits. Right, we do it one by one, and then we put together the results afterwards. Okay, so instead of having 4 stabilizers, in this case here, of weight 2 and 1 of weight 15, we end up with 2 stabilizers of weight 6 and 3 stabilizers of weight 5. Okay, so this is just to say that like the way you implement this code, okay, you're sort of like free to mix and match it. Okay, if you want a full error correcting code, you do need to also correct for phase flip errors, right? But the way you merge and you do the concatenation, okay, depends on what you would like to do. Okay, usually what you can do, you can trade the complication of extracting stabilizers with the many stabilizers you have. Okay, so these are all games that like one can play once you have a theory in mind to simulate. Okay.
Alessandro, can I ask you a question about this?
Of course.
Once you change the stabilizers from that 15 Gauss law check and those 4 green things to the 3, 5 and the 2, 6 checks, the logic qubits are different now, right? The kind of the interpretation of these logical states are more involved or more complicated than the original, like a kind of more natural Gauss law logical states.
In a way, yes. In another way, no. In the sense that, like, even if you stick to this, like, sort of like more physical, intuitive way of extracting stabilizers, okay, your logical states are not local in space.
Right.
Right. So whenever you work imagine you are in these cases here, right? Your logical states that are only these D times M logical states, okay, they don't belong to any given site necessarily because it's been spread out by the Gauss law.
Right.
So this is essentially the same thing. So the logical states corresponding that are stabilized by this set are exactly the same logical states stabilized by these guys.
Oh, really? I see.
Yeah, it's the same stabilizer set.
I see.
It just looks different, okay, but it's really because like the states you have are not local to the site. You're delocalizing them. Okay. What changes between these 2 guys here, if you want, is 1 the stabilizer, but 2 it's also the logical operations. Okay, when you want to do hopping, for instance, okay, it might be easier on this side here than not on the other side here, because then you're going to need to act like on guys that are acting on those guys around. Okay.
So these 2 sets are equivalent.
Sorry, come again?
These 2 sets of stabilizers are equivalent. Is that the statement?
Yeah.
I see.
Yes.
I can do multiplication and to get the other. I see.
Exactly.
Yeah.
So the subspace with +1 eigenvalue on all of these guys, it's the same as the subspace with +1 eigenvalue on all of these guys.
Actually, I didn't see that because the blue, right, the 6 qubit the stabilizers, they involve 2 blue circles.
Oh,
but none of the stabilizers.
I see what you're saying, right? So the idea is that the logical qubits, so the state stabilized, are those where all of the possible 6 guys are everywhere. So here I'm only showing one link, but like you should think of having them everywhere. And the same thing for this guy. Okay.
Oh, I see. Yeah, it's everywhere.
So,
So that, yeah.
right. So you can think of like in the side of on the right, okay, the green stabilizers, they are not coupling physical sites or physical links, they are detached. The only thing coupling them is this gigantic 15 guy, right? With this choice on the left instead, both types of stabilizers will couple neighboring guys, right? But what you want is the collection of all of them on all of the lattice. Right. So the individuals, so then I see your point, like the individual guys here are not enough to be equivalent to that one. It's the collection, is the union of all of those which should give you, which should be equivalent.
Yes, okay, I get that. Thank you. Yes.
Okay, so since it's already like 42 minutes, let me maybe, maybe let me go through quickly here. So the basic idea here is that when you're working on a lattice gauge theory, right? And you perform sort of like a regular encoding of it, sort of like you're using log2 qubits to encode your links. You use 1 qubit for every spinless fermion you have, and then you impose Gauss law on top of it. The physical space you're interested in, it's just a tiny fraction of the full Hilbert space, right? And that's usually seen as a problem. Right? There are methods that are trying to like reduce this embedding. You can try to like directly encode the gauge invariant states, maybe in a given sector, for instance, okay, to save on space, okay. But usually when you do this type of tricks here, there is like a conservation of misery. Like what you are winning in space, you're probably going to lose in time. Okay, sometimes you're lucky, but like in general, that tends to happen. Okay. So what I'm trying to push with like sort of like this picture of quantum error correction as a gauge theory is that the additional space that you have here that you're really trying to remove to make your calculation more efficient is actually helpful. Okay, because you can use it very naturally using the Gauss law. Okay, to protect your physical information. Okay, so it's something to be embraced instead of something to be thrown away. Okay, the trick is that in order to do it, the starting vector space you have, okay, might not quite be large and nice enough to do what you want. So you actually tend to want to do kind of like the other way around. Instead of removing the blue part, you want to add a bit more states, like to do the phase flip, for instance, and work the whole way in the slightly larger one. Okay, and use the fact that like if your physical simulation has some local symmetry, which looks like a stabilizer, and we're gonna go get in a second to like situations where that happens. Okay, then you can actually do this at a reasonably cheap price. Okay, that's sort of like the philosophy. Now, okay, I should probably start to get close. So everything I told you about so far, okay, has been how to encode states, if you want to memory, okay, which satisfies Gauss's law with an recurrent code. Okay, of course, if you want to use a code like this, okay, you actually would like to manipulate the logical information you're stored in there to do something. Okay, just storing a gauge invariant state, it's not necessarily so exciting. You want to use the encoded information to perform, say, a scattering experiment. Okay, now in order to do it, you want to be able to like perform logical operations on top of this. Okay, now of course, on your physical states, applying Pauli operators, you have the equivalent of the Pauli matrices, but the logical Pauli matrices. Okay. Those are helpful, but the issue with those is that all you can do is to move from one stabilizer state to another stabilizer state. What you would really like to do when you do time evolution is to mix stabilizer states, okay? Or in another language, like include magic into the circuit, okay? So one way we found to be able to actually do it, also in our code, okay, is to essentially use a linear combination of unitaries strategy, okay? Where we use, so imagine it like this qubit here, it's our system encoded with our Gauss law code, okay? Where we know how to apply Pauli's, okay? But we don't know how to distill magic. What we can do, we can couple it to a second auxiliary error correcting code where we do know how to make magic, say a surface code, a 513, some other code where we can actually do it, okay? We push the generation of magic states to the auxiliary code, which doesn't know anything about physical systems, Gauss's law, or anything like that. It's only there so that we can produce T states, for instance. We use it to control Pauli operations on our system. Okay, and by controlling the superposition of states that we have over here, we can actually perform time evolution of Gauss gauge invariant operations, which are all the ones that are entering in Hamiltonian, okay, in a fault tolerant way. Okay, so the idea is that the code you develop using Gauss law, it's very nice to store physical information. It's a bit like cumbersome to perform operations, but it plays well with other stabilizer codes. Okay, enough that you can push the complicated parts in synthesis of the gates to those guys, and then use it to perform operations in a gauge invariant way. Okay.
I have a question.
Totally.
So if you have this kind of trotterization, in general, you can have trotter errors that take you out of the physical subspace.
Yeah.
Would this, like, if you do this within this Gauss's law error correction code, does that error correction also help against these trotter errors or no?
That's a good question. So one way to think about it is like all the operations you're allowed to perform on the system are gauge invariant. So that sort of like tells you that like if you can implement your totalization, then every single block in your totalization will be gauge invariant. Otherwise, you won't be able to implement it.
Logical gates are already gauge.
Oh.
Right. So this Pauli here is a logical Pauli. And a logical Pauli sends a gauge invariant state into another gauge invariant state. Right. So in the very moment that you express your evolution in terms of the logical operations of your Gauss law code, okay, you directly wrote it in a way that like every single block is gauge invariant.
Okay.
Okay. That's also helpful. Okay, we're actually going to get there in a second. In the sense that like you can actually write down your Hamiltonian directly in terms of the logical operations. That ensures that like any totalization you do with the logical Hamiltonian, it's by construction gauge invariant. Okay, you can still have errors, but those are like errors that are not violating Gauss law. Right, because you really can't make them using this code. Okay, good, nice question. Okay, so since we're getting very close to the end, let me maybe skip this a second. What I wanted to show you here is that you can actually use, so one way to think about these gauge covariant codes is that they might be nice if you want to run simulations, okay? Part of the problems they might have is that the thresholds might not be as nice as other more established codes. And it's not totally clear at the moment, at least, how one will increase the distance of these codes. Okay, there are ideas, okay, but that's not being pursued too much at the moment. Okay, another way to use this parallel between quantum error correction codes and gauge theories is that exactly as I was saying right now, if you have your initial Hamiltonian that describes, so this one here is like a 1 + 1D Z2 theory with spinless fermions, okay? Mass term, Oppin term with your parallel transporter and electric field term, right? This one here is written in general, okay, where every single operator on its own can break Gauss law. If you rewrite this guy here in terms of the logic, well, first you want to take care of the fermions, okay? So if you do, say, Jordan-Wigner, it's a 1 + 1D, Jordan-Wigner, it's fine, okay? You turn the mass pieces into Z's, you turn the Oppin part only on the fermion side on X exponent. So why? And for Z2, the parallel transporter is just a Pauli X, which is this guy. Okay, so that's like your Hamiltonian for 1 + 1 Z2 gauge theory looks like. Okay, The single operators won't commute with Gauss law. Gauss law in this basis here, it's sort of like three Z's. It's Z on the link, Z on the side, Z on the link, okay? When you don't have any stick charge, okay? But now if you use the barred operations, these are like the logical operations on the code, okay? If you write your Hamiltonian in terms of logical operations, which you know you can do because the Hamiltonian is gauge invariant, okay, you obtain an Hamiltonian, okay, which it's by design gauge invariant. Every single term inside of here is gauge invariant, okay? And you can think of it like if you directly implement this, imagine you forgot about the fact that you had Gauss law, okay? This is just an Hamiltonian on a set of like L logical qubits, which you can directly encode with regular qubits, okay? You essentially iterated out all of the fermions. All there is around here in 1 + 1D is just the links, okay? And the Gauss law constraint, it's gone from the get-go, okay? You are already working in a specific supersession sector of your gauge theory, okay? You save the memory, and it's not possible to break Gauss law because like every state in this spanned by this state here is always gauge invariant. Okay, so that's one way of like thinking about these mappings, because like you can use the quantum error correcting code to find a dual theory to your initial gauge theory, okay, which directly includes the gauge constraints, okay, and allows you to work directly in a subspace which is gauge invariant. So you can forget about gauge symmetry anymore. Okay. So this Hamiltonian here for 1 + 1D Z2 was also derived by other groups by different means. Okay. The nice thing I think about like doing it with another correcting code is that it allows you to see how you would do it in general. So whenever you're able to write a stabilizer code, which is invariant under your gauge symmetry, when you write down your Hamiltonian or whatever other observable you feel like calculating, okay, in terms of logical operators, okay, you directly have an effective dual theory that you can directly encode, and Gauss law constraints are gone, okay, which can be helpful on its own. And since we are getting essentially at the end, let me just like go to anticipate some of the questions you might have at the end, okay? So I spent like the past 40 something minutes talking about Z2, which, okay, sure, it's a gauge theory, but like it's probably one of the least exciting ones, okay? So everything I showed you works well for any spatial dimension, okay? Essentially by replicating what I showed you in 2D, you can do it for whatever D-dimensional system you like, boundary conditions, doesn't really matter, for Z2, okay? And it essentially just looks like a regular repetition code. Okay, you have some way, you have like a bit of freedom in like do concatenation, but that's essentially all it is. Okay, can we do something else like, I don't know, Zn, which is mildly more interesting? Well, so when n in Zn, it's a prime number, okay, and you use qubits, so n-level systems to describe like physical systems to encode your system, okay, it turns out you can carry over almost everything I told you so far, because when you have a stabilizer qubit code, you can turn it almost immediately into a stabilizer qubit code if the dimension is prime. If the dimension is not prime, there are some issues with like reconstructing the right error when you do it. Okay, but if you want to do, I don't know, Z3, Z5, Z7, all of those, again, in any spatial dimensions, can be done essentially with the same construction I told you so far, okay, with just minor modifications of what you need to do to the sites, okay? So if you're interested in this, we almost have a paper out. We are like writing down the last few bits, so we believe like within the month, it should be out. Okay, this covers all of the Zns when n is prime, which it's more than Z2, but like it's still not like all of them, right? In the meantime, we managed to find a way to also include situations where n it's a power of 2. Okay, the construction it works. We are trying to sort of like understand it a bit better, because we do believe you can extend it reasonably easily when you, instead of having like just powers of 2, you have products of primes. And whenever you can do products of any primes, you can do Zn with any n. okay, at the price of introducing different qubits with the right prime dimensions, okay? But so this one here, it's not quite as developed as this one, but we think that like we are probably we should probably be able to like get a paper out like early next year, okay? And we are reasonably confident that essentially one can use these strategies for essentially any ZN, okay? Which again, it's better than just doing Z2, but still like it's a billion. So like what we really care about, especially you guys at the incubator, is to try to do non-abelian theories, okay? So before you ask me about like SU3, continuous gauge groups, you can't do this thing, okay? There are proofs that tell you that like if your code is invariant on a continuous symmetry group, then there are errors you won't be able to fix. So if you want to be fault tolerant, you have to give up continuous groups. So Lie groups are not an option, okay? But you can still try to do a code for an abelian group, okay? Turns out we actually have something which seems like it's working, okay? It's still early on. We are trying it out to see if it's robust enough, but like for small non-abelian discrete groups, we believe we have a way of making it done, okay? With a similar trick to the one that we are using for like the non-prime n, okay? So things are moving, okay, in a direction where like we believe that like discrete abelian groups can be taken care of. Some non-abelian discrete groups probably also, okay? But like stay tuned in the next few months, we are gonna get more things for you. And since it's almost an hour, let me just skip the conclusions. Acknowledge the help of my wonderful collaborators, so Abhishek Rajput and Nathan Vibe, that many of you probably know, and two of my students, Luca Spagnoli and Matteo Turco, and the European Union for like sponsoring the project, and all of you for your attention. Thanks.
Thank you, Ali, for the very nice talk. It seems we need to invite you again early next year to tell us about the new progress. But any question for Ali?
I have a question. So you said you can write down this duality for any dimension.
Yeah.
Do you know what it looks like for Z2 and 2 plus 1D?
It's essentially like this with a complication at like, so there are two steps when you want to write a theory like this. Step number one, you want to find a way of encoding your fermions, right? And the way we are doing it here, and we do it also in the paper with Luca, which is, well, it should be in one of these, yeah, this guy here, okay? We have the explicit two-dimensional one. The price you're paying, if you do general Wigner, that you have long strings of Paulis just to get the right phases, right? So those are there regardless of gauge symmetries, okay? So you can think of like the two-dimensional version of this as exactly this, plus a string of z's, logical z's, which are essentially doing the general Wigner phase, plus the plaquette term. Okay, so you still have some non-locality coming from the fact that like you started from a qubit non-local theory with Jordan Wigner, and you end up again with a qubit non-local theory. The idea is that when you find a dual theory, all you're doing, you're smearing the locality with the size of your Gauss law, which is just the links around the link. Okay, but if you start already with Jordan Wigner, which is non-local, then you already started with something that spreads throughout, so that stays there. Okay. So, and the same construction works for any D. Like you just need to do the Jordan Wigner mapping as a snake, right? The plaquettes are the same, you just have the orthogonal ones. Okay, but if you're interested in the one of the appendices of this paper here, we have the full expression, the full construction for the two-dimensional one. Then it's generalizable in the same way, essentially.
But this duality is different than the standard duality to the Ising model?
Good question. I am not sure. So this one in 1+1, it is the standard one. In more than one dimension, since the weight of your operators is larger, I am not sure. Like the physics is the same, so the same type of phase transition need to be the same phase transition on the other side, right? It might just look different because we use the Jordan Wigner mapping. Okay.
Okay.
But in principle, no one prevents you from using other mappings for fermions, which might still be local. Okay, and you can still pull it off. So in particular for Z2, there are ways where you can essentially do all of this without using error correction and integrate out the fermions and still keep everything local. Okay, they are sort of like equivalent to what we are doing here. Okay, but those allow you to remove the general bigness strings in large dimensions. They only work when you have a Zn where n is an even number. You can remove all the fermions and get rid of the poly of the general bigness strings. If you're interested, like send me an email, I can send you a reference to that.
Okay, thank you.
Of course.
Yeah. I think on one of your slides, you mentioned the non-local stabilizers. Can you say a bit more about that?
This one here.
Right.
Right. So these the details I need to ask my student Luca, but like my recollection of it is that whenever you have a stabilizer code, okay, with finite weight stabilizers, okay, and you make copies of it to get a larger code, okay. If you allow yourself to extend your stabilizers to something which covers, I think, a constant fraction of the full space, that gives you enough power to reduce the total number of qubits you need to for redundancy.
I see.
Okay, so it's a really non-local thing. You're not just meeting it out a constant factor. It's a non-locality which grows with system size.
Right. I see.
Right. That's why it's sort of like impractical.
I see.
Okay. Of course, like there could be like situations in between where instead of taking like the most local possible option or the most non-local possible option, you go somewhere in between and you can win on it.
Yes, right.
Totally.
Yeah.
Yeah.
It'd be interesting to know kind of what the extra, let's say, non-local Gauss law, right? It's not Gauss law, but let's say some non-local constraint we put on top of the local Gauss law. And yeah.
I mean, I think like an easy way to think of it is really like if you take, since this is all abelian, all the Gauss laws commutes with everybody else, right? It's really like saying I'm taking collections of Gauss laws together, which I measure simultaneously. Okay, so it sort of looks like that.
I see. Yes, I see.
Yeah.
Okay. Any more questions for Eddie? Also from the people online. I saw somebody raise up. Henry.
Hi, Elliot. Nice talk. Thank you.
Hey.
So I guess so you were talking about for the continuous Lie group case, how basically there's a no-go saying that you're just not going to be able to correct all of the errors.
Yeah.
But also on a quantum computer, I mean, you're never really going to be able to actually like properly encode like a continuous symmetry on qubits. So would you I mean, you know, but the way you like kind of digitize your continuous group, there's a lot of ways to do this.
Right.
Would you say that trying to develop codes for this is just going to be pretty heavily dependent on the way you do that, or are there kind of general remarks you can make?
So that's a good question. So for the abelian discrete ones, it's sort of simple. Okay. In general, I think all you really care about are the group elements you keep in your discretization. Okay. And so an easy way to think about it is like the Gauss laws you have when you only truncate your continuous group to a discrete subgroup of it, right? They form a basis for your Gauss's law. And what you need to do, you need to try to find generators, okay, of the stabilizer group, which shares the same stabilized subspace as the Gauss laws. Okay, so once you can specify for every link a finite number of possible transformations, regardless of the basis you use to write them, you really just need like the group operators.
Okay.
Okay, then you can use that one there to find a code that matches that, right? But like, so there are also truncations that like actually are invariant for continuous transformations, like on quantum link models, for instance. Right? Those are truncations that preserve continuous groups. Okay. And those ones there, if you wanted to use those, then there is this no-go theorem that tells you that, like, you can't get the full U1.
Okay.
Okay, there are some errors that are not detectable by the code that you're going to build. Okay, that's not to say that like they're not possibly still helpful, because like the no-go theorem tells you that like there are errors that are undetectable, but there is also like an approximate fault tolerance that tells you like how likely it is to get it. Okay, so you can make approximate error correcting code, which can still be helpful, or at least like you can use them to say make these dual theories. Right. Yeah.
Okay. Thank you.
Of course.
Okay, I think I see no more questions, and we're also running out of time. So let's thank Ali again.
Thank you.
Thank you for staying up late.
Of course. Thank you for inviting me. It was a pleasure.
Sure.
Hope to
Okay.
see you in person.
Yeah. Yes. And
That'd be nice.
we'll definitely hear you more in the future when those two papers come out.
Sounds good.
Okay. Have a good night.
Bye.
Thank you.
Bye-bye.
Bye-bye.